Today we are going to talk about Kepler's laws. The laws were published by Johannes Kepler between 1609 and 1619, which described the orbits of planets around the Sun. The laws modified the heliocentric theory of Copernicus, replacing its circular orbits with elliptical ones. The laws also explained how planetary velocities vary.
Kepler's first law. Kepler's first law states that all planets move along elliptical orbits with the sun at one of its focuses. The shape of the ellipse can be described with the eccentricity E. The eccentricity must be greater or equal to 0 or less than or equal to 1. There is the semi-major axis, which is the furthest point from the center of the ellipse, and then there's the semi-minor axis, which is the closest point on the orbit from the center of the ellipse. The point where the semi-major axis occurs is called the perihelion, and the point where the semi-minor axis occurs is called the aphelion, with respect to the sun. The equations of the first law are such that eccentricity E is equal to 1 minus b over a whole squared, where b is the semi-minor axis and a is the semi-major axis. For the second equation, r equals a 1 minus e squared over 1 plus e cos theta, where theta is the angle made by the planet with respect to the in the orbit, while r is the radius of the orbit.
Kepler's second law, also known as Kepler's equal area in equal time law, states that whilst a planet's angular velocity in an elliptical orbit may vary, the angular momentum will always remain the same. For instance, in the figure below, we can see that a planet in an elliptical orbit around the Sun would travel a far larger distance x in the same time it would take to travel the smaller distance, here denoted as y. If you were to draw a line from the planet to the Sun at the beginning and end of a certain time interval, and measured the area enclosed by both lines and the line of the orbit, this area would be the same no matter where you measured it, as shown by area x and y. As observed in this slide, the planet's velocity increases to a maximum as it approaches the perihelion and slows down to a minimum as it approaches the aphelion. As you may see, a line from the planet to the Sun sweeps over equal areas in equal intervals of time. For a small time period dt, the line sweeps over the triangle shown. The area of this triangle, dA, is given by 1/2 times the height r times the base rd theta. So the constant rate at which area is swept over by the orbit is given by dA over dt, which gives us 1/2 r squared d theta over dt, or 1/2 rv theta for a small angle theta. We know that the angular momentum L is given by mrv theta, so the constant rate at which area is swept over by the orbit dA over dt is given by 1/2 L over m, where m is the mass of the planet.
We now come to the third and final law of Kepler's laws of planetary motion. This law states that the square of the orbital period t is proportional to the cube of the semi-major axis a, which can be seen in the formula shown here. This formula states that the square of the time period is equal to 4 pi squared multiplied by the semi-major axis cubed, divided by the product of the gravitational constant and the mass of the object being orbited. This formula can be simplified to only t squared equal a cubed. The quantities in the original formula were expressed as follows: t expressed in Earth years, a expressed in astronomical units, and m expressed in solar masses. As a result, the expression 4 pi squared over g will be equal to 1, and we get that t squared is equal to a cubed. As a result of Kepler's third law, we deduce that the larger the semi-major axis of the object in orbit, the longer its orbital period will be. This is demonstrated in the animation below, where the blue planet, with a smaller semi-major axis, also has a shorter orbital period than the green planet, as the blue planet completes 2 revolutions around its star, in the time it takes the green planet to complete only 1 revolution. We can confirm that Kepler's third law is valid using orbital data for the objects in the solar system by analyzing the graph below. This is a graph of the cube of the semi-major axis, expressed in astronomical units cubed against the square of the orbital period expressed in years squared. It shows the proportional relation between the square of the time period and the cube of the semi-major axis, as the further the planet is from the Sun, the longer its orbital period would be.
In conclusion, Kepler's laws are a good approximation of two-body's planetary system. By predicting and observing the planetary motions and revolutions around the Sun with Kepler's laws, we have better agricultural systems for farmers. By calculating the positions of the Earth relative to the Sun, we can know the change of seasons and temperatures. Furthermore, Kepler's laws are good universal preliminaries. It helps humans sending spaceships and astronauts to explore the universe. The laws plays an important role in the process of human exploration of the space. That's the end. Thanks.